Okay guys, so here we are with the last topic, which is 9, nuclear and particle physics. So for your information, this topic comes with 7 marks for our final PSPM, but we will only be focusing on the first 2 subtopics, which are nucleus and also radioactive. So let's get started. Okay, the first subtopic 9.1, binding energy and mass defect. Okay, so the main character in this subtopic will be a nucleus. Okay, whereby nucleus is made up of protons and neutrons that are bounded together. But on the same time, we need to understand about atom as well, whereby nucleus is located inside of an atom and surrounding by it is electrons. Okay, so usually a certain element is being written as X with the number of nucleons A and Z written on the left side of it. So X represent the elements that we have, such as hydrogen, heliums, lithiums, and so on. Okay, so from the list of equation, number 82, we have A equals to Z plus N, where A is the nucleon number, Z is the proton number, which is also the value of the electrons in the atom, and N, capital N here, is for neutron. Okay, so what we want to know is the mass defect, where the definition of mass defect is the difference in the mass between the total mass of the nucleus and the mass of the individual substance that produce the nucleus. Okay, so we have equation 83 and 85, where we have delta M as in the mass defect equals to ZMP plus NMN minus with M nucleus. Or we can also use equation 85, where we have delta M mass defect equals to ZMH plus NMN minus mass atom. Okay, so here I specifically highlighted the difference between equation 83 and 85, where in 83 we'll be using the nucleus mass, and in 85 we are using the atomic mass. So remember, atomic mass includes the mass of electrons inside of the elements or the particles, right? Where MP here is the mass of proton and MH here is the mass of hydrogen. So you may notice mass of proton and mass of hydrogen is 2 different values. Okay, and in equation 84, we can actually calculate the value of mass nucleus given the mass of atom by taking the mass of atom minus with how many electrons that exist inside of the atom, multiply with the mass of the electron. So Z here is actually the number of proton that I say it's the same as number of electrons. Okay, so if you refer to the list of constant values, you are given the mass of neutrons, mass of protons, and also mass of hydrogens, which also I have emphasized here. Mass between proton and also hydrogen are slightly different. Okay, so take note also, in the constant value, you are provided with 2 different units of the mass, which are in kilogram or in atomic mass unit U. Okay, so depending on the question, if the question gives you in kilogram or in AMU, atomic mass unit, then you will substitute according to the question. Okay, so if you notice, there is a slight difference between these 3 masses. Okay, 1.674, 1.672, 1.673. Okay, so therefore we will not be rounding off these values, and you are advised to use all the digits that is provided in the question. Okay, given that the difference between the values are very small. Okay, so do not round off the value, and also use all the digits that is given. Okay, aside from mass defect, the other quantity that is very relevant to the topic is binding energy. Okay, so binding energy is actually the energy required, okay, either to separate the nucleons completely, or to bound the nucleus together. Okay, so to calculate the binding energy, you have equation 86 whereby binding energy denoted as EB equals to delta MC squared. So here you have to be very careful. If the delta M that you calculated, the mass defect, is calculated in kilogram, that means you multiply with C squared, which is the value of speed of light in vacuum. Okay, 3 times 10 to the power of 8 square. Okay, do not forget the square. So you will get the unit of EB in joule. Okay, however, since there is another unit of mass defect which has been introduced as atomic mass unit U. Okay, so if the value of delta M is in unit U, therefore to get the binding energy, we directly multiply it with 931.5 mega electron volt. So the unit for binding energy when using delta M in U will be in mega electron volt. Okay, so there's a conversion between how we get C squared to become 931.5 mega electron volt. However, I am not going to explain in this video. Okay, so apart from there, from binding energy, there's also another one quantity that is known as binding energy per nucleon. So what does it mean? Simply take the binding energy that can be calculated from equation 86, divide by the number of nucleon A of the elements or the particle. Okay, so this equation EB over A is not provided in the list. Okay, the list end at equation 86, EB equals to delta MC squared. That is all that is given. Not even EB equals to delta M multiplied with 931.5 mega electron volt. So here this value, okay, actually you have to remember, but also this value is in the list of constant. Okay, right? So why this value binding energy per nucleon is important? Because this value measure the nucleus stability. Okay, so if you look at the graph that we have here, okay, this graph shows the binding energy per nucleon EB over A against the number of nucleons A, right? Where here it shows this region here from 50 to 80 actually, okay, where the particles or the elements are the most stable elements, okay, right? Where iron 56 is the most stable element that we have in our periodic table. Okay, so the higher the value of EB per A, the more stable the element is. Okay, alright, so let's look at question to check our understanding.